Hi everyone, welcome to this episode of Keipert Labs. In today's video we're going to be discussing the concept of radioactive decay and introducing the term or the idea of half-life. Okay, so far we've been learning about the idea that some atoms are radioactive or are unstable, and that these unstable atoms, that their nucleus will decay or break down over time, that it will split in half, or it will decay by giving off some form of radiation to become smaller on the quest to becoming more stable. So we've seen it with elements like uranium. We're seeing it with like a whole kind of range of different things more in the upper end of the spectrum of the periodic table. And so today I'm going to model the concept of radioactive decay using these little coloured buttons here to represent atoms of uranium. Okay, now so what I'm going to show you, if you'll bear with me as I kind of get prepped for this, is that each of these, so I've got 24 uranium atoms here, and that as they decay, that they're going to be turned into thorium, which we're going to represent with red. Okay, so that as these atoms decay into a different element, their color will change. Okay, so that's just cluing you in about how this is visually going to work. Because one of the things that we see when it comes to radioactive decay is that not all the atoms of uranium decay at once. This is a process that happens over a very long period of time. And so that suggests that not all of the uranium atoms decay simultaneously, that, after a certain time period, that we only decay, only a certain number will break down. Okay, and so I'm going to basically do an activity here that then we're going to construct a table over on the side here to keep track of how many uranium atoms that we have left. So we're saying that in this exercise that at time 0 that we have 24 uranium atoms. Okay, so that then what we're going to see is that over time, let's say every every 2 minutes or every time period of 2, that then half of our atoms break down. Okay, so we'll go from 24 down to 12. Okay, so now we now have 12 uranium atoms left, 12 blues and then 12 reds. Now what we see is that then if we keep track of it for another 2, we lose some more. We now have 1, 2, 3, 4, 5, 6 left. And now after another 2, we can see we change again. And we have 1, 2, 3 left. And then we have another time period. And we lose some more. And then we get to the 10th. And we lose our last uranium. And there we have it. So we now have 0 left. So what we've seen is that in each of these time periods, that our number has decreased. And we've eventually decayed down to nothing. So that we have only thorium left and no uranium left. Now, hopefully we remember by now that thorium is also radioactive, so then these ones would then be starting to decay into other things as well. But just showing you that we didn't go from blue to red all in one go, but that gradually we got a decrease. And so that as we went from 0 to 2, we went from 24 to 12, so half. As we went from 2 to 4, we went from 12 to 6, so half again, and so on and so on. That we can see that as we went through. Now, there's obviously a little bit of, a little bit of estimation that happens from here to here because we can't have half a button. But we're seeing that as we go over time, that every 2 minutes or every a time period of 2, that then it decreases by half. So okay, and so what we can recognize is that this 2-minute time period is important for the sample that we're looking at here, and that we call it the half-life. So 2 minutes is this term called the half-life. The time taken for 50% of the sample to decay. Okay, so if we started for 24, we looked at the time that it took to get down to 12, and then the time that it took to get down to 6, and then 3, so that then no matter which time period that we're looking at, that then we can see that in this case that we have a half-life of 2 minutes. Okay, so now what that has, it has implications for what we do, or what we need to do with the samples is that not every radioactive element has the same half-life. And so, okay, so that these half-lives can range from seconds up to billions of years for things that are very, very slow. Okay, now, if the time period for 50% of it to decay is in the area of billions of years, then obviously it gets tricky for it. We haven't been measuring for billions of years to be able to know this. So how can we actually find that out? Well, what we can do is that we can say, all right, we can monitor its progress over a particular amount of time. So say if we go, thinking about from 0 to 1 year, and then it goes from 100% to 99.95%. Okay, then what we can do is that then we can say, right, well, if it takes 1 year for it to drop by 0.05%, then we can expand that out and say, right, well, therefore it's going to take this much longer to drop by 1% and by 50% and so on. We can, by monitoring a sample window over a small time period, we can what we would say is extrapolate, or look at the data and then expand its scope to think, okay, well, if it does this much now, then it will take this long to do the amount that we're looking for. And so we can work out these values. Now that has implications or follow-on effects for how do we handle radioactive material. If the uranium that comes out of nuclear power station, or the radioactive material that comes out of a nuclear power station will take billions of years to not be radioactive anymore, then that means that we need to be careful about how we store it. Or deal with that waste, okay? Because then we've got a sample that is still releasing radiation into the environment, okay? And so a knowledge of half-life and how long it takes things to decay gives us useful information about what to do with it, how to treat it, and also information about how safe it is to handle. Okay, thanks very much for watching. Bye for now.